Okay, hello. I hope everybody can see us. This is a joint meetup of the Jacksonville Java User Group and the Jacksonville Google Developers Group, the GDG. And we are very excited to have Barry. And he will introduce himself more, but he has done a lot in the Java community and also in the Google community, from what I understand. So, but the subject is particularly interesting, and a lot of people here are very curious about it, and it is quantum computing and how to approach it from the Java point of view. So you have this emoji at the bottom of the picture. You can use that. Maybe somebody can use it now just to give me indication that you can hear us and see us. Otherwise, please use the messages or the question and answers to send questions. And if there are people here that have questions, I will interrupt or I will interject it from my point of view. So let's get started. I will try to make myself disappear. Here we go.
And now that you've disappeared, I'll share my screen. Here we go. All right, listen. This is not the good old days where everybody is in a room and watching me talk or whoever talk, but I really like sort of interactive sessions. So if you get lost or if you have any questions, please, please, please do whatever Eyal says to do. Raise your emoji or scream out or something like that. And feel free to interrupt me anytime. I love especially the stupid questions because those are the ones I can answer. The others I'm not so sure of. So anyway, this is about Java and quantum computing. I got into Java way back in 1995 when it was in beta, and wrote Java for Dummies in 2000, I think. It's in its 8th edition now, and I have some other Java books too, and I'm the leader of a couple jugs, and I'm a Java champion. My day job is that I teach at a small liberal arts college in Madison, New Jersey, and there's my email address there. Feel free to email me any time of the day or night, and just if you do, all I ask is that you remind me that you were at this session so I know kind of where the question is coming from. And questions about anything are welcome. So I guess we'll get started, right? Here we go. Let me just do introduction. There we go. Look, the first thing I have to do, and I always do this when I give this talk or a talk of this kind, is give a shout out to Johan Voss. He wrote the API for quantum computing. The API is called Strange, and he wrote a book about it, Quantum Computing in Action for Manning. And I always feel indebted to him for giving me the opportunity to talk about his work in these sessions. He does a few of these, but he also offloads some of them to me. And I really appreciate all the work he's done and his generosity in creating this API and in allowing others to use it and talk about it. So anyway, please buy the book, Quantum Computing in Action. I don't get a kickback or anything, but I think it's a worthwhile book, and it's something that it's worthwhile supporting. This is a picture of the internals of, I believe it's IBM's quantum computer. Looks like a lot of circuitry, a lot of gold stuff. This whole assembly, large as it is, will be dipped into a vat of super cooled helium, I think. And the part at the very bottom, I'm going to move here so that pointer options, laser pointer there. Can you see my little red laser pointer? Hello. Yes. Okay. This part here is where the qubits are. This little thing here. This is essentially the quantum computer. The rest of it is controls. So anyway, this whole thing gets dipped into a cylindrical tank down to near 1 degree Kelvin, or maybe less, or maybe a little bit more. I'm not sure. But then, of course, there's an assembly of classical computers surrounding it to run the thing. It's a huge engineering endeavor, and this computer may have only something like 5 qubits, which is like 5 bits to a classical computer. Not 5 bytes, not 5 megabytes, 5 bits. Well, this has 5 qubits, and 5 qubits can do a lot more than 5 bits, but it's still very limited. So that's kind of, there are quantum computers now that have, I can actually run for free on quantum computers with 5 qubits and with 7 qubits. I have to pay money to get up to 50 qubits. There are apparently quantum computers with 300 qubits. It's still in its infancy, but it's working its way into production eventually, very quickly. Here we go. Okay. So you may have already heard about quantum computing. The idea of quantum supremacy is the possibility that quantum computers can solve in a practical amount of time problems that it would be completely impractical for a classical computer to solve. The kinds of computers we have today are called classical computers. So the one that's sitting in front of you, if you're online right now, is a classical computer. Von Neumann architecture. Quantum computers, though, because of the way they work, can solve problems a lot faster. And in fact, it says on the slide, in October 2019, Google, with a computer called Sycamore, claims to have solved a problem in 200 seconds that would have taken 10,000 years for a classical computer to solve. Now, a couple weeks later, a group in China said, no, it won't take us 10,000 years. We can solve it with a classical computer in 5 days. I don't know. The point is that the algorithms for quantum computing make some problems that are currently completely out of our ability to solve with classical computers. Quantum computing makes them solvable. So all we need is the right engineering to make quantum computing practical. We got to get from 5 bits and 100 bits and 300 bits, qubits, that is, up to 10,000 qubits. It sounds like a large leap, but I don't know. I think in about a decade at least, at most, we'll have that. For now, today, quantum key distribution is about to be made commercial. And quantum key distribution is not quite quantum computing, but it uses the concepts from quantum computing to very safely distribute symmetric encryption keys. And the way it does it is it uses the magic of entanglement and superposition to make it so that a receiver and a sender can agree on a key with no transfer of the key between them, and no ability for an eavesdropper to be able to detect what the key is. And that's a technology that's on its way in. In Europe, British Telecom is already got some companies using it, and they're going to go full commercial within a year or so. So that's at least for real. Back in December, well, you can see the slide. Researchers in China claimed to break today's encryption with a quantum computer that's 372 bits. things are on their way. Things are rolling. Here's a list of some companies that are big in the quantum computing world. Most of the work I've done is on IBM's machines, but as I say, I got started with Microsoft's Q#. I haven't used the others much. D-Wave is a notable player because its quantum computers use a different architecture than the one that I'll describe here. All right. I'm sure you're familiar with the notion of a bit. A bit is a concept in classical computing. It's a 1 or a 0, and I'm going to use the magic of animation to illustrate what a bit is. And let me there we go. That's a 0. And the reason it's can you see that it's flickering on and off? The reason that I'm having it flicker on and off is to illustrate an important concept. That concept being that if somebody sends me several zeros, each time I measure it, each time I look at it and try to figure out what it is, I'll see a 0. Now, with bits, that's not important. You're a big deal, you know. Somebody sends you a 0, you see a 0, assuming a good, clean network. So, you know, what if somebody tries to send me a 1? Well, that's cool. And then somebody sends me another 1 and I see it and it's a 1, and somebody sends me another 1. Okay. The idea here is you got to think about repetition. Somebody doesn't send me a 1 0. Somebody sends me 100 of them and I read all 100 of them and I see 0 each time. Or somebody sends me 100 ones and I read all those ones and each time oh yeah, that's a 1. That's good. Okay. That's the way things are in the classical world. And there are classical logic gates. Now, I dealt with this a long time ago. Are people familiar with this sort of thing? And gates, or gates, not gates? Hello, hello. I see yes, yes, yes. Okay, are there any no's? The yeses have it. Okay. The idea is, let's take the AND gate, for example. Let me go back to pointer options, laser pointer, like that. You know, you input a 1 and a 0 comes out. Or if you input a 0, then a 1 comes out. With an AND gate, the only way that you get a 1 coming out is if 2 1s go in. Now, when you program a classical computer, the last thing you're worried about is what gates are on the inside of the processor chip. But when you program a quantum computer, we are at such a low level of development that what you do is you build a circuit of gates. You conceptually describe a bunch of gates and you send the qubits through it. So quantum computing is gate level computing. It's as if you were creating a circuit diagram using these particular kinds of logic gates. But the quantum gates don't look like this. They look a little bit different. Let's move on and see. Oh, here's a demo. I'm going to, yeah, let's do this. I'm going to switch screens. Let me see what I can do here. Boom. Here we go. This is a quantum program written in Java, written using the strange API. Do that. Let me stop that. Let me just do run. Here we go. What have I got here? Well, this is sort of a classical program. It's written in the strange programming environment. Here we go. Okay, where did that? Excuse me while I tinker. There we are. So this is Java FX describing the circuit that I have here. And the circuit that I have here simply sends a qubit that starts off at 0 and it goes through an X gate, which effectively is a NOT gate. Let me enlarge this a bit. See what's happening here is a qubit number 0, starts off at 0, goes into a NOT gate. When it comes out, it's a 1. Since it's a 1, this word on indicates that I get a 1. Big deal. That doesn't look like much, but, baby steps, right? And here's the program. Here's the Java program that makes that happen. Essentially, what we do is we add a gate, an X gate, and then we add it to the circuit, and then we run the circuit, and then we get the result, and we have some text output. It says the value that we get is 1. And let me just make sure that we see that text output. There it is, right down here at the bottom. The output value is 1. And boy, that's not even a hello world program. That's an almost nothing program, but we're going to expand this into real quantum computing. In the meantime, let me just say that this render program line is what makes it so that you can see this Java FX display. So let's see. What am I going to do here? Oh, that's interesting. Okay. I'm going to build you a quantum program. And I'm using the strange Java API to do it. So here in my code, I create, by the way, here in my code, I create an instance of the program class. This is a new program with 2 qubits. The 2 qubits are called Q0 and Q1, and they're both initialized to the 0 value. And for qubits, we're going to use this ket notation that Dirac came up with. It's more efficient than using zeros and ones in ways that I may or may not have time to go into. Now, what I'm going to do next in my program is create a step. So I'm going to declare an instance of the step.
Hello, I was trying to, when I brought Bradley on stage, I was trying to turn this off, and since then we stopped hearing you, Barry. Can you enable your camera and microphone? I don't think I can do that, but it looks like it's disabled.
How am I doing now?
I can hear you now,
And can you see
but I
me?
can't see you yet.
There we are.
Yes. Okay, great.
So
So I'm
you've
going
seen,
to hide myself again,
so you've
and
seen none of this slide, right? Or you've heard me talk about none of this slide. Here we go. I'm going to start it again. Oops, if I can. Let's go back. There we go. Okay, can you hear me now? Everything good? Yes. All right. Here we go. I'm going to create a quantum circuit for you by programming it in Java using Strange. The first thing I'm doing is I'm instantiating the program class. A program is essentially a circuit. In this case, it's a circuit with 2 qubits, 2 wires. There's the number 2. They're called, in this case, Q0 and Q1. And they both start off with what you can think of as a 0 bit, but it's actually a 0 qubit. Okay, yeah, here we go. Okay, they both start off in the 0 state. I'm going to click this button now, and what you see is the next line in the program. I'm going to create an instance of the step class. The step class is just one set of gates that are going to be in this circuitry. So this is called step 0 because I named it step 0. It's a brand new step. It's not part of the wiring yet. It will become part of the wiring soon. But first I'm going to put some circuitry on it, namely a gate. So in the next line of code, I'm saying take step 0 and add a gate to it. And the gate that I'm going to add is a new, and an X gate that's like a NOT gate. It inverts the input. And this 1 means put it on the qubit whose index is 1, not the qubit whose index is 0. So here's qubit 1. I put an X gate onto step 0. Are we good so far? All right, cool. I'm going to create a brand new step. I call it step 1. It's another step in the action of my circuitry. To step 1, I'm going to add 2 gates. The first gate is what I call a Hadamard gate. I'll talk about that soon. I'm adding it to the 0 qubit, the 0 index qubit, as opposed to the 1 index qubit. And that's why it's up here. This X is going to be moved here. This H is going to be moved up here. I'm also going to add an X gate, and I'm going to add it to step 1, and I'll add it to qubit number 1, this one, the bottom one, so it goes down here in step 1. And finally, I have to put these steps on the circuitry. In the program object, I'm calling the add step method that adds step 0 to my program. And then, again, in the program object, I'm going to call add step to add step 1. And when I do that, this goes up here. And now I've got myself a circuit. The circuit doesn't do very much at all. Actually, that circuit is useful, but it's very primitive indeed. So that's what statements in Strange look like in order to construct a circuit. And let's see what you can do with some of these things. Once again, we have bits. We have 0. We have 1. In the quantum world, we have this thing ket 0, KET 0, and ket 1, KET1. If you send me 100 zeros, I'm going to measure them all, and I'll always see 0 when I measure them. If you send me 100 ones, I'm going to measure them all, and I'll always get a 1. And I'll create that by taking a gate that's already been created and just simply putting a not onto it. So I'll just take the 0 that's there by default and turn it into a 1 by putting this X, this not gate on it. Now, here's the secret sauce. There's another thing that I can create that's half 0 and half 1. And in order to create one, I add this thing called a Hadamard gate to my circuitry. And I do it in Strange by saying to a particular step, add a brand new Hadamard gate. And then I specify which qubit it gets added to. Now let me click this button again. Notice what I've got here. Sometimes when you measure it, you get 0. Sometimes when you measure it, you get 1. The weird thing about the quantum world is that when a qubit is in a superposition of states, in particular an equal superposition in this case, then half of the time I measure it, I get zeros. Half of the time I measure it, I get ones. And there's the order in which I get zeros and ones is particularly is genuinely random. I may not always get 50-50. If I do it 100 times, I may get 53-47, or I may get 42-58. But it'll always be close enough to 50-50. And this is the way I define the half and half state. I define the half and half state. My way of thinking about the half and half state, it's called the frequentist point of view, is to think that a qubit that's in the half and half state, half the time you measure it, you get a 0, and half the time you measure it, you get a 1, roughly. And if you measure it only once, you can't tell anything about it. If you measure it only once, you'll get a 0 maybe, and you can't tell where it started. You have no way of knowing because nature collapses it down to a 0. So here we've got a thing that's in an in-between state between being 0 and 1. And until you measure it, even nature doesn't know whether you're going to get a 0 or a 1 when you measure it. All nature knows is that if you measure 100 of them, you'll get approximately 50 zeros and 50 ones. And I'm going to pause for a minute to see if this is in any way sensible or making any sense. I see some little icons floating up from is that? Okay, all right. That probably looks, I see some little, yeah, are we good? Can somebody say in the chat or? Okay, all right. Yeah, that's a nice slide. Okay. That's a good one too. Why is superposition useful? If I have 3 classical bits, let's say those bits are 1, 0, 1. That's binary number 5. And if you don't want to interpret it as binary number 5, you can interpret it as something else. But let's just say we're interpreting it as an int value. That's just one value if I have 3 bits. Now, what if I have 3 qubits? Then if one of them is in a half-half state and the other is in a half-half state and the third is in a half-half state, then conceptually, what's represented there is all 8 possibilities that the 3 qubits can be in. This can be either 0 or 1. This can be either 0 or 1. And that can be either 0 or 1. I don't dare measure them yet, because if I measure them, they may snap to being 1, 0, 1. Or if I measure them, they may snap to being 0, 0, 1. Or snap to being 1, 1, 1. But while they're in this superposed state, there are properties in this arrangement of all 8 binary values that 3 qubits can be in. So whereas a bit represents one value, a qubit represents an exponential number of values. If I have 3 qubits, it stores information about 2 to the 3 possibilities. That's 8. If I have 4 qubits, it stores information about 16 possibilities. If I have 5 qubits, it stores information about 32 possibilities. So the number of possibilities, the number of values represented in a particular superposed qubit state grows exponentially with the number of qubits, and that's enormously powerful. And I see a chat here. Quantum state is a probability wave function. Absolutely. Not going into that, though. Or actually, I might. Which is that's not a question, that's a comment, right? Okay, all right. That's why superposition is useful. How do you make yourself a qubit? These are a couple of the ways. I don't. I heard that you can do the double slit at home experiment with an ordinary laser pointer and a human hair. Well, you can implement qubits with a spinning electron, polars, laser beams, and so on. I don't know much about that. Okay. Yeah. Let's not do this. This is. Oh, here. Yeah. Right. Right. Let me show you another program here. Chapter 4, Hadamard, Maine. Okay. So what we've got here is another Hello World program. It creates a circuit with 1 qubit. The qubit is called Q0. It starts off in the 0 state. It hits one of these Hadamard gates, and by the time it marches to the measuring device, we have a 50% chance of reading a 0 or a 1. And this display is thanks to Java FX. Johan is a Java FX aficionado. So let's just see what we've got here. Quantum execution environment, that's essentially a compiler for this Java code. It's a compiler that compiles it down and turns it into instructions for quantum circuitry. Now, the strange API has not yet been compiled to a real quantum computer. Instead, this is being compiled to a classical computer that's imitating a quantum computer. So that's why he calls this a simulator. Basically, what we're saying is take this Java code that I've created and turn it into code, machine code, byte code, that can simulate what a quantum computer would do. And this is going to work as long as you have very few qubits. That's okay. I'm trying to arrange for someone to help with getting this compiled to CHASM, which is the language, lingua franca for quantum computers, and that would be a good thing. Okay, we create a program which reads circuit. It's 1 qubit. We create only one step. We put a Hadamard gate on the qubit with index 0. We add the step to the circuit, and then we run the program. We get the results and measure it, and we end up getting a value. And the value, well, we ran in, there was a loop here. There it is, mini execution. We ran this 1,000 times, and in 1,000 runs, we got 487 zeros and 513 ones. Just for funsies, let's run it again. We have the same circuit. This time we have 484 zeros and 516 ones. The variation on real quantum computers will probably be larger. But that's just part of the way the game works. That's because real quantum computers are noisy. They're not good enough to do as well with very small circuits as simulators are. Let's try going back to the slides. Okay, there's this other bizarre phenomenon in quantum computing called entanglement. And if you think you understand this, you're wrong. Nobody understands it. Least of all those of us who pretend to be physicists. I don't even pretend. Those of us who fake physicists, right? Hobby physicists who do computer science and mathematics. Let's say that I've got 2 qubits. And I apply Hadamard to one of the 2 qubits, and then I perform an operation that entangles the 2 qubits. So let's say that one of the qubits is in the half and half state, and then I do an operation that says, I'm going to sort of say it. So let's say that QA is in that half and half state. Half the time we measure it roughly, it's going to get 0. Half the time we measure it roughly, it's going to be 1. And I apply a 2-qubit operator on it. I zap both qubits with something so that to the extent that this qubit is 0, this qubit doesn't change. But to the extent that this qubit is 1, this qubit changes from being a 0 to a 1. Now, that's a weird, that's a mouthful. What I'm really saying there is, if qubit A is 1, turn qubit B, leave qubit B as 0. No. Well, back up. Here we go. Start again. What I'm saying is, if qubit A is 0, leave qubit B at 0. But if qubit A is 1, then switch qubit B so that it's 1. Which kind of means that both qubits are 0 now, or both qubits are 1. And there's no other possibility. But remember that before I did this, I put QA in that half-half state. So there's a sort of a half reality that QA is in the one state and that the value of QB will change. So what I do is I send these 2 qubits to distant parts of the galaxy. One of them goes to the Andromeda galaxy and the other goes to the edge of the galaxy. I somehow manage to maintain this entangled state during that travel. Somehow. Theoretically, I can do it. Practically, forget about it. But theoretically, I can do that. I can take these 2 qubits and I can put them in different parts of the universe. And now what I do is I measure one of them. And when I measure it, I could get either a 0 or a 1, but whichever value I get, that's the value that I'm destined to get for the other one. Remember that when they were together, they were either both zeros or both ones. When they're apart, they're either both zeros or both ones. But, and here's the big crazy thing about it. Until I make a measurement of one of them, not even nature knows whether they're both zeros or both ones. And that's been shown by an incredibly clever experiment called Bell's test. So in other words, let's march back. I make one of the qubits half and half. I make them so that they're either both 0 or both 1. I separate them to 2 different parts of the universe. They're either both 0 or both 1, but at the moment, they're still both in the half-half state. There is no natural hidden variable to determine whether they're both in the 1 state or both in the 0 state. That doesn't happen until I measure either one of the until I measure either one of the qubits and find that the other one is the same. Now, this is what Einstein called spooky action at a distance. Nobody understands. These things can be separated by light years, and it happens instantaneously. Nobody knows why. It means that there's no locality in the universe. It's crazy stuff. But what it ends up doing for quantum computing is it makes it so that when you entangle qubits, you can accomplish a lot all at once just by measuring one of them. So if you have 1,000 qubits and they're all entangled with one another, an operation, and now they're all entangled with one another and they're all in superposed states. So you have 1,000 qubits, you have enough information for 2 to the 1,000 different values. You make an operation on one of them and it affects everything, all thousands of the qubits. All that work gets done at once. And I see there's a question in the chat. Feeling very ill. Truly enjoyed the lecture. Oh, sorry. I hope you're feeling better. Okay. So, I mean, entanglement is this extremely strange thing, completely counterintuitive. But what it ends up doing is it means that in addition to qubits being able to be in half and half states and represent more than one value at once, we can also affect one qubit by tinkering with another. And I think we have a demo, Bell state. Okay, so here's what I did here. I did my usual strange API magic. I added steps. Let me move this over here. I added steps and gates and then added the steps to the program. And then I came over here and ran the program, ran the circuitry. And then I measured both qubits. And notice what I did here. First, I applied a Hadamard gate. That's this thing. I put qubit 0. I'm going to make it larger if I can. Yeah. Okay. First, I applied the Hadamard gate to qubit 0. That's right here. Add gate Hadamard 0. Then I applied a gate that conditionally flips qubit 1 depending on the value of qubit 0. That's called a controlled NOT gate. And what that does is entangle the two qubits. So when I get to the end of the circuitry and I measure them, they're in the half and half state, both of them. But if I look down at a graph of what was measured, roughly half the time they're both 0, roughly half the time they're both 1. As a matter of fact, as you can see on the text output, 499 times they were 0, 501 times they were 1. If this were a real quantum computer, there'd be some 0 1s here in the chart and some 1 zeros in the chart, because quantum computers aren't as perfectly. Quantum computers suffer from something called decoherence, which means that as the qubit travels along, it loses its state. So, you can't rely on this clean a chart when you get a real quantum computer. But if we're just simulating what would happen in a theoretical world, and when we get the technology perfected, you have this business where either both qubits are 0 and both qubits are 1, and nature doesn't know which it'll be until we measure one of them. I'm going to stop for a minute, and after I take a question or two or whatever, I'm going to tell you about the threat that quantum computing poses for encryption schemes. Any questions? Anything? Bell inequality being correct with Einstein-Podolsky experiment would not mean faster than light information as long as the measurement chance is exactly 50-50, but if it is not perfect, faster than light info could be transmitted. The Bell experiment has several loopholes that have been worked out one by one over the years. And the only remaining loophole, as I understand it, is that there's either faster than light communication between the two qubits, or there isn't faster than light communication, but what happens in one part of the universe affects what happens light years away instantaneously, so that everything is connected. And now, how we sort out those possibilities, I can only say that I want to be a fly on the wall decades from now when they have it all worked out. Please explain Bell's test if possible. Okay. I'm going to try to give you start with these two qubits. And you examine them in the middle of their paths to distant parts of the universe. You don't examine them, you think about them in the middle of their paths to two distant parts of the universe. And you ask, if this one knows that it's 0 right now, and this one knows that it's 0 right now, and you measure these two qubits at different angles, when you get them to their destinations, what's the probability that you'll see a 0 here and a 0 there? And it turns out that if you measure them if you measure a 0 at a different angle, you don't necessarily get a 0. Because you see, you've got a light ray that's sort of oriented this way, and polarized sunglasses, you measure at an angle, and it comes out to a probability here. So you're in the middle of sending these 2 qubits to their destination, and you say, if this one is 0 and this one is 0, and nature knows that they're both 0, what's the probability that you'll get certain values when they hit sensors at different angles over here? And that probability, if we can say that this is 0 and this is 0 in flight, that probability turns out to be greater than 5/9, greater than or equal to 5/9, which is definitely greater than 1/2. But quantum theory and experiments have determined that indeed it's not greater than or equal to 5/9, it's 1/2. It's an extremely clever argument, and that might be the best I can do right now. When you think quantum computers when do I think they'll be viable for ordinary computer users? And what do you think of security issues you said about anything? Well, I'm thinking in the next well, first of all, you can run a quantum computer program right now. You can run it on IBM's hardware. I do it every day. It's got 5 qubits. You can't do much interesting with it, but it's certainly interesting from the point of view of quantum computing, and they're real quantum computers. When will we be able to do it to do useful things? That's going to be another story. I mean, ordinary consumers will probably be under the hood using some kind of quantum key distribution within the next 5 years, but they'll be doing it from their own classical computers, and it'll use quantum key distribution somewhere along the way. In terms of when you'll be able to sit down and write a Java FX program and take advantage of quantum processor, a QPU under the hood, I don't know. I'm gonna guess 20 years at the least. But hey, who was it who said there will be 1,000 computers at most in the world? This is just all guesses on my part. So let me just talk about security, because I promised to finish it at 7:45. I think I said 7:45 and not something else. I promised to finish by 7:45. There are 2 aspects here to security that we got to be aware of. One of them is that we can very safely distribute symmetric keys using quantum computing concepts, and that's very much on the horizon. That's coming in the next year or so. On the other side of the coin, if we have good quantum computers with, say, 10,000 qubits, we can effectively and easily break RSA encryption quickly. Let me show you a slide or two. So this fellow named Peter Shor devised this algorithm that allows us to break lots of encryption schemes that we currently use today very easily. And could you please give some example for practical use of quantum computers and how that would benefit over classical computer, especially in ML and AI? let me get to that in a few. Let me just talk about this, and I promise to address that question in a minute. Look, multiplying two numbers, a times b, is easy. If you have a very large number c, finding how to factor it is computationally difficult. If you know about intractability and polynomial time, it's probably not even in polynomial time. And that's what a lot of encryption schemes depend on, the difficulty of factoring numbers into two prime numbers. Okay. For example, this is a cute slide, and I don't know what was motivating me when I put it here, but it's just so cute. If you take this number, you can factor it into this number, and those are both prime numbers. I'm not sure what use this slide has, but it's you don't want to try to get a computer to factor this number. On the other hand, if you know this number and you know this number, you can multiply them together pretty quickly. So the whole thing that makes cryptography, asymmetric cryptography, secure, or at least some schemes of it, is this notion that it's difficult to factor numbers. So let's take a look at some factoring here. I've got the number 15, and I want to factor it, and I don't know what its factors are. It's such a big number, the number 15. My gosh, how could I possibly factor 15? Well, I pick a number like 2, and I take 2 to the 0 mod 15. And then I take 2 to the 1 mod 15. And then 2 to the 2 mod 15. And then 2 to the 3 mod 15. And then 2 to the 4 mod 15. And I notice I get 1 back. And as soon as I get a 1 back, the pattern starts repeating. So 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. There's a repetition there. And that's going to happen no matter what two numbers I start with, 15 and 2. And look, what's the period of the repetition? The period of the repetition is 4. Oops, back. So what am I going to do here? Let's say that I have a way of finding out what the period of repetition is. I don't know how to factor 15. I don't know that it's 3 times 5. But I do know that if I take 2 and take it to different powers, then it starts repeating after a period of 4. Well, first what I'm going to do, I'm going to take my number 2 and my number 4, and I'm going to do 2 to the 4, and then I'm going to divide it in half and subtract 1 and get 3. And then I'm going to do the same, but add 1. And I'm going to get 5. And looky here, the two numbers that I got, 3 and 5, those are the factors of 15. So if I know what number I started with here, and I know what the period of repetition is, then I can, at least with this method, calculate 2 prime factors of the number that I want to factor. I don't know I know that in the beginning that 15 is 3 plus 5, but I can find that out, right, by taking the number 2 and the number 4 and doing this arithmetic with it. Now, it doesn't always work, but it's a very high probability of working. And I have some other examples, but you could try this yourself. The trick now is taking a sequence of numbers 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and finding out how often they repeat. Now that repetition pattern might be 10 billion instead of 4. It might be, 60 billion, billion, billion. It might not be easy to find in the classical world. But in the quantum world, you can apply this thing called a quantum Fourier transform. And a quantum Fourier transform is essentially a set of gates that tells you what's the period of a repeating sequence. It's essentially done by taking a repeating sequence and looking at it in a certain different way, which is what they call the change of basis. Let's take a look at this equation. X squared plus y squared plus 5x minus 2y minus 17. I don't know, that's very nice, right? What if I take that expression and I look at it in a slightly different way? I look at it at a different angle. So what if I let a equal x minus 2 and let b equal y minus 3? Well, then, if I do the algebra, it turns out that this is simply a plus b. So the idea here is if you take a repeating sequence, you express it as a sequence of qubits, and then you apply a certain operator to it that looks at it a different way, then you end up getting the period of the sequence. So let's just take a look quickly at one thing. Someone said earlier in the chat that a qubit is a wave function, and indeed it is. If I have two waves, I can combine them. If I combine this wave with this wave, then it just becomes a bigger wave. If I combine these two waves, because the trough of one is in the same place as the peak of the other, and the peak of one is in the same place as the trough of the other, when I combine those two waves, it just gives me something flat. So what do I do conceptually in order to find the period of a sequence? I take the sequence with period 4 and I apply different period waves to it. Now this is a metaphor. This isn't quite what happens, but this is kind of what's going on. When I add together the period 2 wave with the period 4 wave, I get something like that. Not too interesting. When I apply the period 3 wave and add it to the period 4 wave, I get something like that. Again, not very interesting. Now, what about this one? If I apply the period 4 wave to the period 4 wave, I get this nice thing, and that's going to stand out. In fact, that's going to tell me that the sequence that I started with was a period 4 sequence. And that's called the quantum Fourier transform, and that's pretty much the most that I'm able to tell you in the time allotted. Was this session recorded? I joined late. Yes, it is being recorded, right? That's pretty much all that I have time to tell you. But the idea is, if we can use quantum computers to factor numbers effectively, that we got to come up with some brand new encryption schemes. And in fact, the government is working on them. It's called post-quantum encryption, and they're extremely elaborate. There are 4 candidates right now, and they're trying to find out which ones are the best and the most effective. I want to get to Gunnar's question. Could you please give some example for practical use of quantum computers and how that would benefit over the classic computer, especially in the ML and AI world? Okay. Let's go to a different model of quantum computing. You're talking about ML and AI, so I'm going to guess that you know about deep neural nets in machine learning. So a neural net is a bunch of nodes. Each one of them sort of behaves in a way like a neuron in the human brain. A bunch of inputs to the nodes. The nodes have inputs to other nodes, which have inputs to more nodes, which have inputs to more nodes. The configurations of the nodes become extremely elaborate, and the output is eventually going to be something like, this is a picture of an apple, or this is a picture of a cat. So you input the pixels for a picture, and it goes through all these nodes, which the nodes make other nodes fire, which make other nodes fire, which make other nodes fire. And eventually you get this report here, whether this is an apple or a cat. And the trick in machine learning is to adjust the behavior of the nodes so that they fire or don't fire at the right times. So you start with this thing getting all the wrong answers. Then you say, in supervised learning, you say, no, that wasn't a cat, that was an apple. And so the neural net kind of tweaks the values of the nodes and changes how one node affects the next node, and the weights and the firing patterns of one node and the next node. And eventually this thing learns to distinguish an apple from a cat. And there's so much research in that these days, and it's very effective research. I mean, ChatGPT must have some of this under the hood for it. Now, the quantum version of that is to take each node and not make it a 1 or a 0, but to make it a qubit. And there's a lot of research going on in that, and it seems to be very promising. Another model for quantum computing, again, it's not the gate model, is to create a collection of qubits that, when it calms down, finds a minimum configuration. And that's called quantum annealing, and it's proved to be very effective by the Z-Wave company in solving optimization problems. It doesn't solve general problems in general very well, but it's very good at optimization and doing those problems quicker than a classical computer can do.
Anybody here has any comments or questions?
Natasha asks, in order to learn more about this topic, what would you suggest? Get Johan's book. It's called Quantum Computing in Action. And it's a fantastic intermediate level introduction to quantum computing. And if you have questions for me, You see my name is over here at the right. I'm going to point to it. There it is. Yeah.
Your name is there, yes.
Yes, I can see it. I'm just enjoying pointing to something that's virtual. You can reach me at Barry.
It's the other way.
You can reach me at barry@burd.org and ask me anything you like. And it says there are a few questions.
Randy has a question. You want to
Okay.
come? Okay, there is a question. 1 second. What are other models beside the gate models?
Oh,
you mentioned that there are some.
Two of the models are that machine learning model, the neural net model, and also the quantum annealing model. So the machine model is you make yourself a neural net, but each element of it isn't 0 or 1. Each element of it has a superposition of 0 or 1 in it.
Right.
And the other model is quantum annealing. There, what you've got is a bunch of qubits that sort of cool themselves into a stable state that ends up being minimum. And there's a lot of progress with that. Z-wave is
there are also quantum. There are also quantum genetic algorithms, which apparently have been around for a while, but
okay, all right.
I know very little about it.
I haven't heard much about that. Do you? Yeah. Do you know what kinds of problems they've been used to solve?
I don't know what problems in particular. There are genetic algorithms that solve generally optimization problem. I presume that it's a lot like the annealing, because annealing, simulated annealing, and genetic algorithms in the classical way, they solve all kind of black box optimization problems of many types. So taking the annealing to the quantum is probably very similar. The things you would do with genetic algorithms when you take them to the quantum, but I know no more than that. I hope to get into it soon.
Genetics plus quantum. What more can you? How much more can you pack into technology? It's a.
Then you can add fuzzy logic to it.
Yeah, that's it. That's it. What else? Are there other questions?
Not here.
Anything in
Thank
the
you.
Q&A?
You've done a great job.
And next week I go back to the spring semester at the university. And yeah, I don't know what courses I'm teaching yet next week, but I'll find out when I walk into the classroom. I hope.
Thank you, Barry. It was a pleasure having you. It's a great subject, and you did a great job with it.
Thank you.
And we'll be happy to have you again in the future. And this has been recorded.
I
So
enjoyed myself thoroughly.